Like I thought you I guess it was. I guess it was. You know, like jobs or something. Environment. Kind of was. Yeah. So that's
also good. So you can't tell me how you can read these forms.
Yeah. And then like I'm gonna go to Peru or something, and that's gonna go. And
So I sent you an email yesterday. Sorry, I didn't respond to the survey.
Oh, that's it.
I didn't think I probably should respond to surveys since I'm very easy to.
Oh, that's
Wires right?
Yeah. Thanks. So.
I guess we can get started. Thank you all for coming to the dissertation defense, Paul Hegedus. I had to start writing things down because there were so many things that I wanted to say to introduce Paul, because you know, he was an undergraduate here. He came out of our department, and he's had this history that's been wonderful. And as you get to know Paul, you start to realize he has all these skills that are quite impressive. And when Kathy Zabisky was his major advisor as an undergraduate, I remember asking her about Paul as a student. He was doing very well in my course, and I said, you know, so what about this guy? And she said, well, you know, he's impressive. You should get him to work for you for the summer. So I kind of hit him up and said, hey, you want to work for us in the lab? And then learned that we could offer him $10 an hour, and he could be making $18 an hour driving a Bobcat on a crew with doing landscaping. So there was no question about the fact that he refused me, and right then and there I knew he was a lot smarter than I was. so that was good news. Then he took my weed ecology course, and in that one day I gave a lecture on modeling herbicide resistance, and he came up after that lecture and said, hey, I'm interested in these models, and you know, could you show me a little more about them and stuff? And I said, yeah, sure. You know, nobody's ever interested in seeing models and simulations and things like that. So especially at the undergraduate level. So he came by my office and we talked a little bit about his interests, and I showed him the model, and he said, oh, that's pretty cool stuff. And I said, well, you know, something I've always wanted to do with these models, and that was I'd never taken the approach of really mechanistically showing the outcomes of the interaction of individual plants when they have a certain genotype or shared phenotype, and how that actually progresses through a population. And he said, oh, that sounds pretty cool. And he comes back a few days later and said, hey, well, I read up about this a little bit, you know, I'm really interested. And so we wrote a proposal to the Weed Science Society of America, and he got an undergraduate research award for doing some research on this project, which allowed him to also go and present to the national meeting as an undergraduate. And truthfully, people were astounded at that work. It was really cool. And that and especially when they found out he was an undergraduate. And so he had great potential for going on to graduate school. He had many choices as to possible places to go. Thankfully, he decided to stay at MSU. Thankful for me, I think I tried to convince you to maybe look at other places, but I wasn't in much earnest there. It was like, please. Well, and probably Meg was here, so that really made the decision. But anyway, Paul decided to stay and did amazing things. And among them, he was able to get a Western SARE Graduate Student Fellowship Award, which was great to help pay his way. And he really was the primary author on a set of Montana Fertilizer Advisory Committee proposals that we did for 5 or 6 years, 6 years probably in a row. And we were successful in all of those, only failed in the last one, which was the best one. but what a great record as an undergraduate, so, or as a graduate student. So Paul did all these wonderful things and really basically wrote up a publication of his work as an undergraduate. I should have said that. We didn't publish that paper yet, but it's still on one of those burners back there. So these are all things that I think are indicative of Paul's success, and I just can't say enough about his work ethic, his commitment to these projects. He's basically held together a national level project that's the data intensive farm management project that comes out of University of Illinois. He's kind of the primary technician on the project, but he's really been the glue among so many people. And whenever there's a problem, they end up calling Paul and he fixes it. And many times I don't even know that he's doing these things. So this has been impressive, and again has resulted in many people across the country chomping at the bit to get their claws into him as a postdoc, which he's kind of wisely holding them off. So that's all cool. How could you go wrong with a guy that can operate heavy equipment, can write our code till the cows come home, and can do all these amazing statistical kinds of approaches and then write it up and produce papers like crazy. So Paul, thank you, and we're looking forward to your presentation, Optimizing Site-Specific Nitrogen Fertilizer Management based on maximized profit and minimized pollution. Thank you.
Cool. Thanks, Bruce. Thank you all for being here. Yeah, just want to start off by thanking my advisors, Bruce and Stephanie again, everybody on my committee, my wife Meg, my lab mates, Sasha and Hannah, and really everyone else who helped me over the past 4.5 years. And so today I'm going to talk about 3 out of 7 chapters of my dissertation that really address my main goal, which was optimizing site-specific nitrogen management based on maximized profit and minimized pollution. And so first, just a little bit of background, depending on where you're from and your background, what you think about when I say farming could vary. You might think of what we call subsistence farming, which is characterized by farm sizes about 5 hectares or less, where you're growing a variety of crops to either feed a family or a local community. Or you might think of what we call industrial agriculture, which is more characterized by heavy equipment and chemical inputs, where fields sort of stretch on for as far as the eye can see, what you might think when you go up into the Golden Triangle of Montana or the Corn Belt of the Midwest. But no matter what the farm size is, there's many different things in between. They're all important for humans because they provide the food that we eat, fiber for our clothes, feed for animals, and then biofuels such as ethanol. And so, as you can see, everywhere that we practice agriculture, we also apply nitrogen, whether it's organic forms like manure or synthetic forms like urea, et cetera. But we're applying it all across the world, basically in every type of farm system. And so, as you can see, everywhere that we're applying fertilizer, we're applying nitrogen in excess of crop nitrogen needs. But the distribution of the over application of nitrogen fertilizer isn't quite equal. The United States, China, and India account for 2/3 of all excess nitrogen fertilizer applications. And this has environmental effects. So I don't know how many of you have heard of the dead zone in the Gulf of Mexico, but over-application of nitrogen fertilizer contributes to eutrophication of waterways. And on a more local scale, we're seeing over-application of fertilizer contributing to soil acidification. We've seen it in 24 out of 56 counties in Montana, where excess nitrogen decreases the soil pH, which limits crop productivity and can induce things like metal toxicity. Over-application of fertilizer can also contribute to nitrate pollution. So 1 out of 5 wells in the US has nitrate levels above the EPA threshold, which has detrimental human effects like causing cancer and blue baby syndrome, where a baby can't get enough oxygen and turns blue. So obviously not good. And so besides just the human effects, over-application of fertilizer is also threatening these natural resources, soil and water, which future crop production relies on. And so part of the reason that there has been this over-application of nitrogen fertilizer is that nitrogen fertilizer has typically been pretty cheap. And so on the y-axis here, we have the dollars per ton of urea. Then on the x-axis, we have months. Different colors here represent different years. And as you can see, over the past couple of years, the price of nitrogen has almost tripled. And so farmers not only need to think about applying nitrogen more efficiently in terms of the environment, but also their own economics. So that brings us to the main goal of this dissertation, which was, can we optimize nitrogen fertilizer rates based off of maximizing farmers' net return, but also minimizing the value of nitrogen loss or minimizing pollution? And so this has led us to developing this on-farm precision experiments framework at MSU, which is a cyclical adaptive management process that we can apply to any agronomic input. So for example, I use it for nitrogen fertilizer management, but my lab mate Sasha is using it to manage seeding rates in organic systems. And so it's a 6-step process. The first step is you need to create a database management system to hold all the data that we gather from farms and other open sources, but it really starts with the designing of a variable rate experiment. So we design an experiment, we give it to the farmers that we work with, they go out and they apply it, and then we gather their yield and grain protein concentration data from their combines. We combine that with a bunch of open source data that we gather, like remote sensing and other things, put it all together into a data set that we can use to develop crop response models for yield and protein, which we then use to simulate management outcomes, generate our optimized fertilizer rates, and then give those to the farmers along with comparisons to other management scenarios so that the farmer can make the decision. And then they can either carry on with what they've been doing, use our optimized rate, or decide to go a different direction. But ideally, they apply some sort of mix of our optimized rates plus experimentation so that we can keep repeating this process. So we get more data to improve our models, to make better decisions. I don't know if I should do that. Whatever, we'll roll with it. Anyway, I just want to emphasize the point that what we're doing here is really engaging farmers in the research. So we're applying experiments on a field, and then we're giving decisions to a farmer so that they can make decisions about their own field. And so this brings us to the 5 principles of the OFPE framework. First, that experiments are intended to inform management on the farm fields that are conducted.
I'm listening to Paul
Those online, please.
to a PhD dissertation.
Hey, Chuck.
Hey, Chuck, will you mute yourself, please? Thanks.
Sorry.
You're fine. The second principle is that we only use information that a farmer will have access to, whether it's their on-farm data or open source data. And we only use data up to the point that they need to make a decision on their inputs. Third is sort of related to the first, where we develop our response functions on a field-specific basis. And then every year that we get new data, we can update those models and improve them. And then the fourth and the fifth are that we simulate management outcomes under weather and price uncertainty. And then we give farmers probabilistic outcomes so that they can make decisions off that. So we're trying to make farmers better gamblers by giving them probabilities and the chance. And so just to highlight this first principle again, we're developing experiments for a field to make recommendations on that field. So we're not trying to make recommendations even on a field that's right next door or down the road or the farm next door. And this reduces information loss when we're making management decisions from small plot studies or greenhouse studies. Second, this second principle where we're using on-farm and open source data, we're only using data that farmers are gathering from their equipment, so from their normal day-to-day operations. We're also gathering data from the bunches of satellites that are orbiting the Earth, and then from open source data sets that we can get from Google Earth Engine. And then again, like I mentioned, we're only using data up to the point that a farmer needs to make a decision. So in Montana, with nitrogen fertilizer, farmers are usually applying that in March. And so we don't want to be using data in our models that is gathered past March, because in a future year, when they get to that point, they're not going to have access to that data. So we really constrain that data to what we actually have and what a farmer will have. And so just some examples of the open source data that we get. We gather things like vegetation indices, topographic variables, weather-related variables like precipitation or growing degree days. And then we also are gathering some soil data. And as technology improves, we're going to be able to get better resolution and more accurate data. And depending on the system that you're working in, you can adapt this OFPE framework and either add data, subtract data, substitute data. So it's a really flexible approach. And so then the third principle is that these crop response functions that we're developing are made on a field-specific basis, and we update those every year. And this really contrasts what's been happening in the literature and industry with developing functions for the response of yield, for example, to variable rate nitrogen fertilizers. And so a lot of these approaches have been using small plot studies, greenhouse experiments, and when they do use on-farm data, they're compiling it from a region or across the entire United States or across the world to try and develop a generalized model that they can apply in any field to make recommendations for your nitrogen fertilizer. And so they're really going for a silver bullet approach, which we see is not really working. And so part of the reason that we can't develop a generalized model for this is that response data to variable rate nitrogen data is pretty messy. And then it also varies within a field, it varies between fields, and then it varies for a given field across time. And so this is really a data science problem where we have to use our knowledge of ecology and agriculture, math and statistics and computer science to gain knowledge from this messy data to make actionable insights like recommending nitrogen fertilizer rates. And so then this brings me to the first chapter I'm going to talk about, chapter 4, where not only do we need to characterize the response of yield or grain protein to variable rate nitrogen well, but we also need to make predictions in upcoming years. So we need to forecast what yield and protein will be when we don't know what future weather conditions are going to be. And so the objective of this paper, the main objective, was to compare forecasts from 5 different types of predictive models. And so the first one that we used, we took a similar approach as those other models I showed, nonlinear regression, but we used this beta function from this Yin et al. Paper, has a sigmoidal form with 2 inflection points that was developed as a growth curve model, but because yield is related to growth, we've adapted it for that. And then we've also adapted it to use for grain protein. We also use a generalized additive model, which is a flexible semi-parametric model that we can use for characterizing these noisy data sets. And then we use 2 Bayesian approaches. And so we chose to do 2 Bayesian approaches because that 5th principle of giving farmers probabilistic outcomes fits well with the Bayesian base and probability. And then the cyclical adaptive management process of the OFPE framework really fits well with the Bayesian approach of updating your priors every year that we get new data. And so we used a nonlinear regression approach developed by Bruce's previous PhD student, Patrick Lawrence. We adapted it for protein since it was developed just for yield before. And then we use a multiple linear regression approach. And then the last model we use is a random forest regression, which is a machine learning approach, which is probably the most commonly applied machine learning approach in agriculture. And so to test this objective, we used 7 fields from 3 farms in Montana, where we selected those fields based off their involvement in the OFPE project. So we only selected fields where we've applied an experiment for 3 years and gathered data. And then also based off the quality of data we get from those farmers, as well as their sort of geographic distribution in wheat growing regions of Montana. So again, we go out, we apply experiments. We've done this in 3 years, gathered their yield and protein data and the open source data, and then put it all together in data sets that we can use to fit these models. And so because we're trying to forecast what crop responses will be in future years, we use this hold one year out cross-validation approach, where because we have 3 years from each of these fields, they're in a crop fallow rotation. So either we have data from 2016, 2018, and 2020, or 2017, 2019, or 2021. We use 2 years for training our models, and then we hold one out for testing so that the model hasn't seen that before. And then we fit each model for every field, for every iteration of those. And then our metric of performance is root mean square error, which we use just because it's simple to interpret. The units are the same as our response. So for yield, kilograms per hectare, and then protein, our error estimates are in percent. And so because we're looking at what is the best model for forecasting, we take the average RMSE across these data cases for each of the fields, so that we get an average ability to predict future crop responses. And so looking here, we've got the darker shading indicating the lowest RMSE, and then the lighter shading representing the second best RMSE for each field, and then each of the different models that we tried. And so as you can see for our yield forecasts, the random forest regression tended to do the best in 6 out of 7 fields, while the Bayesian nonlinear regression did best in 1 out of 7 fields. And then in general, just Bayesian approaches tended to do second best for predicting yield. And then looking at protein, again, we sort of have a similar story where the random forest regression tended to do best, only in 4 out of 7 cases in this case, but 3 out of 7 fields, it was the second best model. And then contrasting with the yield forecasts, the Bayesian models didn't really do well. In 2 out of 7 fields, the GAM did the best, and then the beta function did best in 1 out of 7, but second best in 4 out of 7 of the fields. And so just some takeaways from this chapter is that the random forest regression machine learning approach tended to do the best, but the main conclusion really comes down to a very ecological answer of, well, it depends. Depends on the field. And so this really fits well with this OFPE principle that we need to be selecting these models on an annual basis because it varies across fields. And then Patrick Lawrence has also found that it takes about 6 to 8 years to parameterize at least his model, which we could assume is the same for the rest of them, assuming that the climate of the past is going to be similar to the climate of the future, which might not be a safe assumption. And so every single year that you get more data, you might want to reevaluate what the best model is. And so once we have our predictive equations for yield and protein for a given field, what you can do, or what we do, is for every point in the field, we predict what the yield and protein will be for every nitrogen rate, for example, from 0 to 150 pounds per acre, so that we get a distribution of predictions across every point. And then we can calculate the net return. This net return is really the metric of interest for farmers. It's what they make decisions based off of. Basically, how much money are you going to make? And so we calculate net return as yield times the price received for your wheat, minus the cost of nitrogen, times the amount of nitrogen applied, minus fixed costs, which include everything related to agronomic production, like fuel, electricity, labor, rent, etc. Basically everything except the fertilizer and seed. But farmers in Montana, the price received for their wheat isn't only dictated by yield, it's also dictated by protein. And so this varies by elevator, but we've used data from the Billings elevator where they give you 2 cents more on your base price for every half point of protein above 11.5%. And then they take 8 cents off for every half point of protein below 11.5%. So it really pays to have higher protein. And so once we have our net return for every point in the field, for every nitrogen rate, we can go and we can find either a full field optimized nitrogen rate or go along a point by point basis and find our site specific optimized nitrogen rates. However, the main goal is not only to maximize net returns, but also minimize the pollution potential or reduce the amount of the value of nitrogen loss. So we really need to know something about nitrogen loss and efficiency. And so that brings me to chapter 6, where we ask, can subfield nitrogen use efficiency be estimated on a subfield scale using our on-farm and open source data? So the objectives here were to evaluate nitrogen use efficiency using intensive soil and plant biomass sampling, and then develop a predictive model for nitrogen use efficiency in our small grain winter wheat dryland systems. So again, we used fields from the OFPE project. We only sampled in 4 fields. We did 2 in 2020, 1 from the Golden Triangle region, and then 1 field from near Billings. And then in 2021, we selected another field from a different farm in the Golden Triangle region, but then a different field, even though on the same farm near Billings. And so what we did is we went out and we took 75 sample points per field, twice per year. And so we collected data at 5 depths. We went out before a farmer applied their nitrogen fertilizer, their top dress nitrogen fertilizer. Then we went out in June. We took plant biomass samples when crop growth sort of maximized before it starts drying out. And then we came back in the week after harvest and took another set of soil samples. And so we have an inventory of before the farmer applied fertilizer, and then an inventory of nitrogen after the growing season. And so we stratified these samples, not only based off of our experimental nitrogen fertilizer rates, but based off of information from Adam Sigler's work, where we know that nitrogen loss is maximized, or nitrogen loss is dictated by soils management and weather. And so after fallow and with high precipitation events, and then also low water holding capacity. And so because management, like your crop rotation, is affecting the whole field, weather is uncontrollable, we stratified samples based off of an estimate of water holding capacity that we developed, which is just based off of NDVI and the variance of NDVI on a pixel basis across time, where we assume that if productivity is consistently high across different weather conditions, then we would have, then it would be a high water holding capacity, because no matter what the weather is, the crop is getting enough nutrients and water. And then the inverse case, where if it's consistently low across time, we assume that there's low water holding capacity, because no matter the weather, it's not getting enough nutrients and water. And so first, looking at efficiency, we looked at fertilizer use efficiency, which is simply the amount of nitrogen taken up by the crop, which we gathered from our plant biomass samples, over the amount of nitrogen fertilizer, so our as applied experimental rates. So on the y-axis here, we have the nitrogen taken up by the crop. On the x-axis, we have the as applied nitrogen, and then different colors here represent different fields. And what we see is pretty expected ecological response, where as nitrogen fertilizer increases, crop nitrogen uptake increases until it reaches its crop nitrogen requirements, and then it starts to level off. And so as we would sort of expect with that sort of saturation curve, when we look at fertilizer use efficiency on the y-axis here, and then as applied again on the x-axis, we see this exponential decay curve where efficiency is really high at low fertilizer rates, and then as fertilizer rates increase, your efficiency decreases. And a commonly cited statistic is that fertilizer use efficiency is about 33% in cereal grains across the world, which is something we see where this curve sort of levels off. Our fertilizer use efficiency is about 0.3. And so what I really want to highlight here is the scale of fertilizer use efficiency. where a value of 1 indicates perfect efficiency with this metric, so that the amount of nitrogen in the crop is exactly equal to the amount of fertilizer that we applied. And so we're seeing that at low nitrogen fertilizer rates, the crop is taking up more nitrogen than fertilizer we applied, which is indicating that there's internal nitrogen sources such as mineralization, which Adam has estimated can be up as high as 34 kilograms of nitrogen per hectare. And so we revised our sort of estimate of efficiency to calculate what we call nitrogen use efficiency, which is the same numerator, the nitrogen taken up by the crop, because that's either giving value to the producer in the current year, or that stubble that's left in the field can be mineralized and contribute to crop nitrogen uptake in future years. So we consider those efficient over nitrogen sources. And so again, because we're in crop fallow rotation, there's no fixation. We assume deposition is 2.92 kilograms per hectare, which is the same estimate that he estimated in his thesis. Sorry. And that's estimated from the cast net station up in Glacier. Again, our nitrogen fertilizer rates, and then nitrogen mineralization. And so because we didn't measure this directly, we used this simplified model from Vigil et al. In 2002, where he compiled a bunch of data from mineralization rate studies to develop this. And so this uses our total nitrogen measurements from our soil samples that we collected. And so now on the y-axis, we have nitrogen use efficiency. Again, 1 would represent perfect efficiency. So we're seeing now that we're not getting that. On the x-axis, we have the as applied nitrogen, and then different colors show different fields. And so we can see some field-specific variation in nitrogen use efficiency, which is likely due to differences in total nitrogen across the field that we use to derive this nitrogen mineralization number. But in general, what we see is the same relationship, where at low nitrogen fertilizer rates, you got a higher efficiency, and as that increases, you get a lower efficiency. And so again, this is really indicating that there's internal nitrogen production, which I just want to illustrate by looking at the proportion of total nitrogen inputs. And so the scale goes from 0 to 1, where 1 would indicate 100% of the nitrogen inputs, which is just the denominator of our nitrogen use efficiency equation. So different colors here represent those different components. And as you can see, when you apply no nitrogen fertilizer, all of your nitrogen sources are made up by mineralization and deposition. But as you increase your fertilizer, the proportion that's contributed by mineralization decreases because you're applying more and more fertilizer, and your total nitrogen sources increase. And so, now that we've evaluated nitrogen use efficiency in our systems, we wanted to develop a general predictive model that we could use in our fields. And so before you guys finish sharpening your pitchforks, I know that contrasts the field specificity that I've been harping on, but it's because we're trying to fulfill the other OFPE principle of only using low-cost data for farmers. And so it's not really feasible for a farmer to go out and take 75 soil samples twice per year, plus plant biomass samples, get those analyzed, and develop these models. So we're trying to use our open source data and on-farm data that we've been gathering. And so this diagram here shows the relationship between nitrogen use efficiency, the parameters we use to calculate that, and then our open source data. And so orange circles just are sort of a coarse classification of the different data types that we gather. So soil characteristics, weather, and topography, which influence things like mineralization and nitrogen crop uptake. And so similar to what we did with the crop response modeling paper, we're testing 6 different models here. The first 2 only use nitrogen fertilizer as a predictor, so we're violating some independence there, but we're going to have that nitrogen fertilizer data when we want to make decisions, because a farmer can say, I want to apply this amount of fertilizer, we can plug that into the model and get an estimate for what efficiency will be. And so the first one is just simple linear regression using nitrogen, and then the second model was a nonlinear regression, which just mimics that exponential decay curve we saw in the FUE versus as applied nitrogen function or figure. And then the other 4 models, we use our open source covariates plus the nitrogen fertilizer. And so we tested multiple linear regression, a generalized additive model again, and then this time we used 2 machine learning approaches, random forest regression, and then support vector regression. And so again, similar to what we did with our crop response modeling, we're using a hold one out cross-validation approach. However, this time we're holding one field out. And so again, our metric of performance is RMSE, and we hold one field out at a time and then use the other 3 for training. So basically the model is predicting what nitrogen use efficiency is in a new field or what it hasn't seen before. And so for every model, we test all of these iterations, and then we take the mean across those because we want a general model. So how well does it predict nitrogen use efficiency in all 4 of these new fields that it's looking at to identify the 2 best models. And then we use those 2 best models in a 5x2 cross-validation approach, where we use data from all of the years, but you split it 50-50, one into a training set and a testing set. You train your model with the training set and then develop an error estimate and variance from your test set. Then you swap those data sets. So you use the other 50 for training and the other for tests. So you get another estimate of error and variance. And then you repeat that entire process 5 times. And so what this does is it gives us a statistical comparison of which model gives us better prediction of nitrogen use efficiency. And so again, looking here, similar figure to what we showed with the crop response models, darker shading indicating the model with the lowest RMSE, and then lighter shading, which is sort of hard to see. The second best model. First thing I want to highlight is that across our fields, a different model was the best for predicting nitrogen use efficiency. So we're seeing that field specificity again. But again, we're trying to develop a general model that we can use in all of our fields. So looking at the average RMSE, we see that our 2 machine learning approaches, support vector regression and random forest regression, tended to do the best. So we use those in our 5x2 cross-validation. And again, because now it's using all of the data split 50-50 multiple times, our RMSE decreases, but the difference between those is only 0.0013. And so that corresponds to no statistical difference in the accuracy of predictions from those 2 models. And then again, just sort of to demonstrate that, looking at nitrogen use efficiency on the y-axis here, and as applied nitrogen on the x, where the colors represent the different predictions from the models, and then black points are the observed nitrogen use efficiency with different shapes for fields. We see that predictions from the 2 models are pretty much the same. But we concluded that the support vector regression is probably our best bet, just based off this hold one out cross-validation where it had a lower RMSE, because here we're testing how well did that model do at predicting nitrogen use efficiency in a field that hasn't been in the training data set. And so just some takeaways here. Although we saw some field specificity in the response of nitrogen use efficiency with as applied nitrogen rates, the trend typically was the same, or it was the same across all those fields. And so we can reasonably predict nitrogen use efficiency with a general model that uses our Onfarm and open source data, which is our support vector regression. And we know that in an ideal world, we'd have a quick, low-cost way to measure things and develop a field-specific model, but we don't. So we're using the support vector regression to get at our question of how much was the value of nitrogen loss to do this optimization problem. And so this brings me to the last chapter I'm going to talk about, where we pull everything together to optimize these nitrogen fertilizer rates. So asking, can we improve farmer net returns and reduce the amount of nitrogen applied in a field using site-specific management with our on-farm precision experiments approach? And so the objectives here was first to develop those site-specific nitrogen fertilizer rates, and then evaluate the probability that site-specific management is more profitable and reduces the pollution potential compared to other management strategies. And so this really brings in the 4th and the 5th OFPE principle, where we're simulating management outcomes in different weather and price conditions, and then giving farmers probabilistic outcomes that they can choose from. And so again, we use our 7 fields that we used for our crop response modeling, but again, we want to simulate what management outcomes will be under different weather conditions. So we run simulations in an average, a dry, and a wet year for each field. And so on the y-axis here, we have precipitation. On X, we have the year. We've gathered precipitation data from a couple different sources, NASA's DayMet and University of Idaho's GridMet. But just due to some data reliability and data gaps, we decided to go off the GridMet. And so I think this is field D2, but we selected 2001 as the dry year to simulate, 2009 as the average year, and then 2019 as the wet year. And so to simulate management outcomes in weather uncertainty and price uncertainty, we have to use sort of a big simulation approach. And so once you selected the field that you want to get management recommendations for, and then the weather conditions you want to simulate, again, we do the profit maximization approach where you simulate your yield and protein for every point in the field for every nitrogen rate. In this case, we're 0 to 180 kilograms per hectare. And then again, you want to calculate your net return. But because a farmer won't necessarily know what the economic conditions will be in a future year, we use a Monte Carlo simulation where we've gathered economic parameters for our nitrogen or our net return calculation from 2000 to 2021. And then we repeatedly sample those 100 times so that every time we're going through and selecting an economic condition, we calculate net return, and then we can find our optimized fertilizer rates. And that gives us a distribution of outcomes for different management scenarios. So the management scenarios that we compare and give to the farmers is a situation where we apply no nitrogen, a situation where we use the farmer selected uniform rate, our site specific rates, and then we also get a full field optimized uniform rate. So if you could only apply one rate across the field, what would that optimized rate be? Another scenario where we apply the experiment from the most recent year that we experimented in that field, just to see sort of what was the cost of our experiment. And then a situation where we apply no nitrogen and we do a 15% reduction in yield, but we assume that the farmer's already transitioned to organic, so we give them the organic price. And so we have a distribution of outcomes, but every time that we go through a repetition of this Monte Carlo simulation, we keep track of the proportion of times that the site-specific approach generated a higher net return compared to the other ones. So in this little example here, compared to applying no nitrogen or our experiment, the site-specific approach would have been more profitable 100% of the time, compared to a farmer selected rate would have been more profitable 83% of the time, compared to our full field optimized rate 64% of the time, and then only 3% of the time the site-specific approach would have been more profitable than the organic. And so that's really how we do with the profit maximization, but we also need to take into account efficiency. And so we just have to amend this process a little bit. And so when we're predicting yield and protein at every point for every nitrogen and fertilizer rate, we also use our support vector regression model to calculate nitrogen use efficiency or predict nitrogen use efficiency. And then for every repetition of this Monte Carlo simulation, we use the economic parameters sampled to calculate the value of nitrogen loss, which is the cost of nitrogen times what we call nitrogen use inefficiency, which is just 1 minus nitrogen use efficiency, times the amount of fertilizer applied. And so we get a similar curve where we see net returns across all of our nitrogen fertilizer rates, where variation is because we're doing this for every point in the field. But then we're also doing the same thing for the value of nitrogen loss. And so we can use that to find what our optimized fertilizer rates would be when taking into account the trade-off between net return and the value of nitrogen loss or nitrogen use inefficiency. And in this case, your optimized rates would probably be around 67 to 100 kilograms per hectare. Do the same thing where we're keeping track of the profitability across all those repetitions of the Monte Carlo simulation. But again, because we want to look at the potential for pollution reduction, we also keep track of the total amount of nitrogen applied across the field for every repetition of this simulation. And so now that we've developed these optimized fertilizer rates, we want to evaluate how well the site-specific approach does compared to these others management strategies. So on the y-axis here, we have the average probability across fields and across Monte Carlo repetitions that the site-specific approach generated a higher net return compared to our different strategies. So applying no fertilizer, farmer-selected uniform rate, the full field optimized uniform rate, if we applied an experiment, and then that organic scenario. And different color bars represent the different weather conditions that we tested. And so what I want to highlight here is that in an average year, the site-specific approach across all fields and repetitions of that Monte Carlo simulation had a 100% chance of generating a higher net return compared to applying no nitrogen fertilizer. But in a dry and a wet year, the site-specific approach wasn't always more profitable, indicating that sometimes you would make more money if you just didn't apply any fertilizer at all. Second, I want to highlight the comparison to the farmer-selected rate, where across all weather conditions and fields, we saw that there was a 100% chance that the site-specific approach made more money than the farmer-selected uniform rate. And then finally, I just want to highlight the comparison to the full field uniform rate, where we see that the site-specific approach wasn't always, there wasn't a 100% chance that it would make more money than applying just the full field rate. And so sometimes it pays to just apply one rate across the field instead of varying. So the take home here is that the site-specific nitrogen management always makes more money than the farmer-selected management. And then again, we wanted to look at the pollution reduction potential. So on the y-axis here, we have the average probability across fields that the site-specific approach applied less than or equal to the total amount of nitrogen across the field as our other strategies. And so a higher bar here would indicate that there's a higher chance that the site-specific approach was more efficient, applying less nitrogen than the other management strategy, while a shorter bar indicates that there's less of a chance that the site-specific approach is reducing the total amount of nitrogen across the field. So again, different colors represent the different weather conditions. And then first, I want to highlight that compared to applying no nitrogen fertilizer, in an average or a wet year, the site-specific approach always applied at least a little bit of nitrogen fertilizer. So there's a 0% chance that the site-specific approach was applying an equal amount to our zero rate scenario or our organic scenario. But in a dry year, there was about a 14% chance that the recommendations from the site-specific approach was a uniform rate of 0. And so it was applying the same amount of nitrogen as applying no nitrogen. And then compared to the farmer-selected management rate, so a uniform rate that the farmer would have selected, we see a 43 to 57% chance that the site-specific approach was applying less nitrogen. So in total, it's sort of a 50-50 flip of a coin on whether the site-specific approach is going to apply less nitrogen than what the farmer would have been applying. And then comparing to the full field optimized approach, it varies depending on the weather condition, but the site-specific approach isn't always applying less nitrogen than a full field approach. So that's likely due to the variability in the site-specific nitrogen fertilizer rates, where it might be applying a bunch in a little bit of the field, whereas the best rate on average across the field was lower. And so just to reiterate some of the takeaways from these chapters, crop responses and the most predictive model to characterize those and predict those varies across space and time. So we need to evaluate those on an annual basis. We've shown that support vector regression does well at predicting nitrogen use efficiency using our on-farm and open source data. So it's a reasonable, at least initial start at predicting nitrogen use efficiency on a subfield scale. There's a 100% chance that the site-specific rates would be more profitable than farmer-selected rates, but only a 50% chance that the site-specific approach applies less nitrogen than a farmer-selected approach. And so just some general conclusions. Shown that these principles of applying experiments on a field and using data science to give farmers field-specific recommendations has sort of successfully demonstrated that we can increase efficiency in terms of economics and to a lesser degree nitrogen. But as technology develops and our ability to apply precision ag increases, we'll be able to get better data and make better decisions, start eating away at this huge chunk of anthropogenic nitrogen that we're contributing to the global nitrogen cycle, which is going to have benefits for growers, people like us, as well as the environment. So yeah, thank you all for coming, and grilling commence.
Questions?
So I'm surprised that the GAMs perform so poorly.
I know.
And I've been thinking about that a little bit since you've been talking and wondering, how did you decide on the size of the splines? Are they overfitting to the training set?
So we tried to reduce overfitting. We used thin plate shrinkage splines. So we're sort of combining the model or the feature selection and fitting process. But yeah, I mean, I was sort of surprised too, but they might be a little too flexible. And so we might need to play around with the parameters in that to try and reduce the wiggliness of those, because I think overfitting is likely the problem with those GAMs.
And I mean, how did the underlying data behave? I mean, what were the distributions? What did they look like?
So they weren't quite normal. Obviously it varied depending on the field and depending on the year. But sometimes they were bimodal, sometimes they looked normal, and sometimes they were sort of somewhere in between, with wide tails, et cetera. So it really varied depending on the field. And so that might also have been contributing to the issue of, when it's trying to fit a couple years at a time and those distributions look different, it doesn't know how to handle that.
That makes a lot of sense of why the random forest.
Right.
Similar question, I guess. Why did you choose the models you chose? Can you talk more about why you chose the models you chose? I think you mentioned like simplicity, so you chose a random forest, right? Because it's just common.
Yeah.
But then you chose a support vector machine in the next example, which is super, kind of common, but extremely hard to understand what's going on within the algorithm. So like, why choose certain models over others?
Yeah, I mean, of course, it's sort of subjective. Some of those we chose because they're similar to what other people have done in the past. Some of them, like our selection of the nonlinear, that beta model, was because not a lot of people use or adapt growth models to look at yield versus nitrogen curves. As far as choosing the support vector regression, we were just sort of looking for another machine learning approach that's also sort of similar to fit, like the random forest regression, that you can put parameters into. And because with our nitrogen use efficiency, we initially thought it was going to be a little bit simpler and not putting in all those covariates. So where it's trying to find the hyperplanes between data, we thought that might be useful. And it ended up working, yeah.
So one thing you found too is that each model did, better one site or whatever, but you're trying to do a general prediction. Why not use an ensemble?
Yeah, so I mean, random forest is an ensemble model, but yeah, looking at different types of models and putting those together is definitely something that we need to look on for future work.
There were some hands that were raised as well.
Yeah.
Oh, yeah.
Let's go to that.
Scott, you had a question.
Yeah, great presentation, Paul. Thank you. And just following up on some of the modeling questions, as I recall, your first chapter, Bayesian approaches worked really well for predicting yield, but not at all for predicting protein content. Can you speculate as to why that happened?
Yeah, I mean, first, one of the Bayesian approaches that we used was developed for yield in the same fields that we were working in. So that was Patrick Lawrence's model. So I had a leg up there. But I think it also contributes to sort of the scatter of the data. I mean, our protein data is more sparse. It's only gathered on a 10-second interval, whereas the yield data was on 3 seconds. So there's more variability in the yield data. And then we also tend to see more of an actual response curve in the protein data compared to the yield data. And so I think that beta function, where it had the sigmoidal shape and had 2 inflection points, it could capture that curve a little bit better than the Bayesian approach. And then I think also just based off the priors we're using, like for the multiple linear regression, we just started with uniform priors. So I think there's definitely the potential for those to get better over time as we parameterize those more.
And McLean raised his hand up.
Claim.
Thanks for noticing, Stephanie. Great talk, Paul. Paul, can you define what you mean by pollution potential again? And if it's inversely related to NUE, can you tell me any problems that might have, or any poor assumptions that there might be between equating NUE and pollution potential?
Yeah, so pollution potential, we're defining essentially as nitrogen use inefficiency, like you were mentioning. So the inverse of nitrogen use efficiency, where we're assuming that any nitrogen that's not going into the crop is an inefficient use because it's not going to farmers' value. And so I agree, yeah, there's definitely some issues with that because nitrogen that doesn't go into the crop isn't necessarily lost. So if it's dry, the nitrogen might not be leaching out of the soil zone, or if there's not enough moisture, it might not be denitrifying. So we are making an assumption that if it's not going into the crop, it's lost and it's potentially contributing to pollution. So that's why we try to say the potential for pollution and not strictly defining it as pollution.
Okay, thank you.
There's a couple more raised hands.
Yeah. David, your hand is raised.
Go ahead and ask, David.
Thanks. I was on mute there for a second. Paul, which is rare for me. Paul, great job. And just not just great job here, but I've seen just all the things you're doing and you've just done so well. So congratulations on that. As an economist, I think a lot about maximization and profit maximization. And here you're using NUE, nitrogen use efficiency, as sort of a major measure, right, of the goodness of some strategy, right? And nitrogen use efficiency is nitrogen over yield, right? So that's what economists call average product, okay? Can you go back to that diagram where you showed the optimal social amount of nitrogen? It was, you had a bar that was to the left of where the profit, there we go. Yeah. Okay. So what's going on there is you're choosing where the slope of the black curve equals the negative of the slope of the blue curve, right? Because one's a good thing and the other's a bad thing. And that's the optimal. Now, what's that got to do with NUE?
Yeah, so I think you mentioned that NUE is defined as the amount of nitrogen in the crop over yield.
Right.
We're defining nitrogen use efficiency as the amount of nitrogen in the crop over our nitrogen sources, so deposition, fertilizer, and mineralization. So the ratio of nitrogen in the crop to inputs.
Not output.
Yeah, not yield.
Well, you want to be, then I get it. You want to, I think, figure out if you can use a better term when you submit this, because usually NUE means something else.
Yeah, there's a lot of definitions.
Because if it's average product, right? If you want to maximize NUE, you should put on zero fertilizer.
Yeah.
Right. Then you've got yield divided by zero.
Yeah.
As the NUE. Okay, good. I didn't realize that there was a different definition there. Thanks.
There's another couple here.
Yeah, let me see. Klein
is up again.
Let's see. Klein, your hand is raised. Was raised, or is that from before?
Yeah, I forgot to take it down.
No.
Okay, there's still another one.
Lila.
Hey, Paul and everyone there. Nice to hear your work. I congratulate you on all what you have done. Definitely this excels in all the work done around nitrogen. And I think you tackle, two major things, the nitrogen use efficiency as one metric that to me has to be better explored for incorporating some of the other goals that we want to attain for nitrogen management. And the second important, I think, is the protein value. And I think that you accomplish a lot of that with your work. I would just ask you a question on how was the timing of nitrogen application, if you have any thoughts on timing and splitting when it comes to protein content, as it might have a lot of impact right on the translocation of that nitrogen into that source rather than growth and yield. So do you see any potential for further improving our DIFM designs, or perhaps adding that timing as also another way of improving efficiency?
Yeah, so you raise a good point there about the timing of fertilizer applications, and that's not something that we looked at in this research. But I mean, that's sort of the next step of where we're varying nitrogen fertilizer spatially. The next step would be varying it temporally or with space and with time. So varying it across space in one application and then again in another application. And so in terms of the DIFM work, yeah, I think that's definitely somewhere we can go. And this year, actually, we've just designed a couple trials where we do have split applications, I think in Oklahoma or Arkansas. So we can take a look at that.
Awesome, thanks.
One more? I think there's still one more. Oh, okay.
No, that's
Sorry,
loud.
back of the room here.
Do you mind pulling up the sort of like spring map web thing that you made that the orange circles going?
Oh, yeah.
In thinking about this, were there specific attributes of management strategies that you noticed affected nitrogen sufficiency more than others? Like, I'm sure that you talked a lot about climate and weather variations, but I'm sure that soil type, tillage history, whatever other land applied pesticides or herbicides are happening would probably all affect these results. Did you notice anything that like really jumped out as a larger variable than others?
Yeah, I mean, because we're working in conventional systems, I mean, they're all applying herbicides, get rid of weeds, but that would definitely affect it if we're in more of an organic system. And then again, because they're typically in a crop fallow rotation, we didn't see too much variation in management. So a lot of these fields were sort of homogeneous in the way that they were managed. And so I think, yeah, another next step would be looking at nitrogen use efficiency across a broader spectrum of management types, where maybe farmers have a rotation in there, or organic systems like Sasha's looking in, to take a look at that influence of management on nitrogen use efficiency.
But you didn't see that like clay content or carbon content had like pretty significant.
So another thing that I probably should mention is that we're developing predictive models, and so we're not looking at inference, so it's sort of hard to say. But when we fit our final support vector regression model to all of the data and look at what are the parameters that stayed in there after feature selection, we were seeing that clay content would stay in there, same with pH, soil organic carbon would stay in there, and then pretty much all of the soil characteristics stayed in the model. So they were definitely influencing what those predictions were, or at least helping to characterize that.
Yeah, makes sense.
Right.
So similar, like no sensitivity analysis, because you already know those things are important, but you're creating this awesome database, or in building this awesome database. Will it be open for inference? So you can maybe parameterize the models better, or just to increase the knowledge of how these systems are working?
Yeah, I mean, the database is there and we can make it accessible. We'd have to privatize, farmer information for security purposes. But I mean, yeah, moving on to looking at sort of inferential conclusions and not just prediction, sort of more of an academic exercise rather than the applied focus that I've been doing here. So I can let you play around with it if you want.
Let me add it.
You want more work?
Was there anything?
Maybe
Adam, you had a quick.
Yeah.
Sure. Yeah, great presentation. Body of work. I have kind of a high question about just perceptions and a comment you made about helping farmers be better gamblers. It's interesting. The amount of scatter around in response around the main lines is dramatic, right? And so I'm wondering if you have any anecdotal observations about how people are making decisions, and if some of those extreme outlier events are really influencing people's perceptions, and how that might relate to people's interest in adopting these probabilistic approaches to decision making, which on average in the long term are going to be better, but then there's this human perception piece that's influenced by that scatter.
Yeah. Yeah, so the way farmers make management decisions is almost as variable as the data. I mean, Chuck, for example, he likes to use this data and he sort of looks at the yield and protein to figure out sort of an estimate of how much nitrogen he thinks he lost and then reapplies that. Whereas other farmers just buy their fertilizer and ask the fertilizer guy, hey, how much should I apply? Others look at like Clayton Jones's work with extension and go off those recommendations. And so, yeah, I mean, we're trying to make farmers better gamblers, but we also need to definitely increase the perception that the data that we can gather from fields is useful. And so I think there's some statistic out there that farmers make money 1 out of every 10 years. And so basically they're managing for that 1 year that they make money every single year, just in case that they get that. And so, yeah, sort of engaging with farmers, showing them data, showing them the variation, showing them how this data can be used in a probabilistic sense to make them better gamblers, I think is definitely the next step too of, getting this out there and convincing farmers that there's other ways to make decisions.
All right. Yeah, that's what we want. Thank you all again for coming, and the committee will stay and we'll ask some questions.
John Paul.
Thanks, guys.
How you doing? Great job.
Hey, Pat, we're gonna switch to the other Zoom link for the next 3 hours.
This camera wasn't.
It was pointed to begin